Hey guys, I'm back with a new video. In this video we'll start with the implementation of logistic regression. So let us first understand the dataset that we will be working with. So the dataset is iris.csv, and here what is given to us is that you are given sepal length, sepal width, petal length and petal width. You have to predict whether the flower belongs to the category of Iris setosa or it belongs to a category which is other than the setosa, which is whether it belongs to the setosa category or it belongs to a non-setosa category. So let us first import the required packages that we will be requiring to solve this problem. So first I will import, so I'll leave a comment here, import the required packages. Import CSV, import numpy as np, import matplotlib, and then from matplotlib import pyplot as plt. Now let us define a function to basically read the data from the file path. That is, we want to read the dataset row by row using a function, and that function is the same function that we have defined in other projects. So I'll define a function read data. I will leave a docstring comment here, and I will say reading the dataset row by row. So I'll say def read data, and this will take a file path. And now first what we need to do is we need to open the file using the open function. So I will say open, and the open function expects a file path that we are receiving here as an argument to our read data function, and we want to open the file in the read mode, and this will spit out an instance that we can work with. So I can say file object. Now using this variable in our code, we will be able to read the dataset row by row and able to manipulate it if we want. Now let us first define a variable for our predictors collection, or our input variables, which in this case is sepal length, sepal width, petal length and petal width. So I will say x array of arrays, so like this. So this is our predictors collection. So I'll leave a comment here, predictors collection. Now let us define another array for our output response variable, or our output variable, which in this case is category to which the iris flower will belong. Remember, we are interested in separating the setosa category, which is designated by the label 1, from other non-setosa categories, which is designated by the label 0. So for that I will define an output variable and set that to an empty array. Now let us initialize a CSV reader that will help us to read the dataset row by row. So for that I will say reader equals to CSV, and on the CSV we have a reader method, and that reader method expects the file object that points to the file path from which you want to read the file. So the file path will basically point to the file or to the dataset file, which is iris.csv, and you will be able to read the dataset, which is a CSV file, row by row using the reader method defined on the CSV package. We will use the same for loop which we have written multiple times in our previous projects. So using for loop, we will be able to read the row in our dataset one at a time. So I will say for row in reader, and for extracting out our 4 input variables, which is sepal length, sepal width, petal length and petal width. So first I want to extract the values for sepal length and store it at x of 0, which is this. So all the sepal lengths will go here, then the sepal width, then petal length, and at the last index where we are having an empty array for now, we will store the petal width. So we can again use a loop within the outer for loop. So I can say for I in range 0, 4, and here I will say x of I dot append float row. So let us understand what we are doing here. So for row in reader means at the very first row. So for the very first iteration you will be referring this row. So row is your very first row, and in the very first row each time you are going over 0 to 3, for x of 0 you are appending float row of 0, which is this one. So row of 0 will be, this will refer to as a row for the very first iteration. So temporary variable row will point to this row, and row of 0 will be 5.1. So at x of 0, in the very first iteration I is pointing to 0, you say x of 0 dot append float row 0. So you move on to the second one, you say I will get increment by 1, and then x of 1 dot append float row 1, so which will be 3.5. so this will get stored in x of 1. So this is x of 1, and you are appending the value of 3.5 to that, and then I will get incremented by 1, so I is now 2. X of 2 dot append float row 2, so it is 1.4, and then I will become 3 in the next iteration. So x of 3 dot append float row 3, which is 0.2. Now once this is done for the very first row, now we need to handle this output response variable for the very first row. So I can go down, and within the outer for loop only, I have to extract output category. So 1 is for setosa and 0 is for non-setosa. If row of 4 on the current row, which is this one, if it is iris setosa, then append a 1 to our output response variable array, which is holding the output response variables for our dataset. And if this is something other than this, or it's a non-setosa category, then you will append a 0 to your collection of output response variables. So very simple check. If row 4 is iris setosa, then I will say y dot append 1, else y dot append 0. And now once this is done, this entire code is done within the outer for loop, we will move forward to the next row, which is this one, and we will apply the very same logic here as well. We will grab all the predictor values for the second row, which is 4.9, 3.0, 1.4, 0.2, append them in their correct positions, and then if the current row's output response variable is iris setosa, then you will append a 1 to the output response variable collection, otherwise you will append 0. Now once your entire dataset is done with this for loop, you will have all the values for predictors in your x variable. So the very first predictor collection will be present at the index 0, which itself is an array. Then the second predictor collection will be here, the third one will be at index 2, and the fourth one will be at index 3. And all the response variables will be stored in this y variable. So this is your response variable collection, which will have iris setosa or a non-setosa value, which will have either value 1 or 0. 1 represents the iris setosa and 0 represents a non-setosa category. So now in order to prevent the memory leaks, we can close the file by saying file object dot close. Now let us perform the normalization of our input data. For that, I will define an array of mean. Here we will store the mean values for all the predictors. So what will happen is that in the very first column, this one, you will find the mean value. In the second column, you will find the mean value. Third column, you'll find the mean value. Fourth column, you'll find the mean value. And whatever mean value you get for each of the columns, you will append them in your array of means. And same for standard deviation as well. So I will say for I in range 0, 4, because here we will be focusing only on these 4 things, which is our predictors. Okay, so for that I'm using a simple for loop, and I will say x of I, and I will say np dot array, and you can convert that to an umpire array, so x of I, and then you can say mean dot append. So you will compute the mean, so you will say np dot mean, and whatever mean value you get, you will append that to the mean variable, okay, or mean array that we are defining here. So np dot mean, and here we will pass on, and similarly we can compute the standard deviation, and I will say standard deviation dot append np dot std and x of I. And once this is done, I can return a normalized input data. So I can say return np dot array, and I will say x of I minus mean of I. I will wrap this in parenthesis, divided by stdi, again wrap this in a parenthesis, And here we will be using list comprehension. So I will say for I in range 0, 4. Okay, and then you will be computing these values for all of your predictors. So what will happen is when I is 0, you will say x of 0 minus mean of 0 divided by std of 0, which is the normalized value for your input data. So once the very first predictor is done, then you will move forward. So now let us see whether this function works or not. So I will say x, y, mean and std. Here we need to return the array of our response variable collection and the mean that we computed and the standard deviation. Okay, so we will expect these values. So your normalized input data, which is this one that we computed using list comprehension, and then we got the response variable collection, the mean and the standard deviation, and we can say read data, and here I can say /iris.csv. so I can print x, y, mean and standard deviation to the console, and let us run the file by saying python logreg.py. Press enter, and here are the values that we are getting. So you can see this is a big array, and here first you are getting your array of input data. So you are having the predictors, so normalized values, then coming down you get your response variable collection, then you get the mean values. Okay, so this is a small list, so let us correct that because it's not matching correctly, and let us rerun the file python logreg.py. Okay, so here we are getting our output response variable collection. So the sepal length for all the points that we are given to us will get stored here, the sepal width for all the rows, the petal length and the petal width. Okay, so this is your predictors collection, and then we are getting an array of means, which is this one. Okay, because we are having 4 predictors, so for all the columns you are getting the mean values. For the first column the mean is this, for the second column mean is this, for the third column mean is this, and for the fourth column mean is this, and the standard deviation for the first column is this value, the standard deviation for the second column is this value, the standard deviation for this column is third value, and the standard deviation for the fourth column is this value. So let us define a function for a gradient descent function that we implemented in the multiple linear regression, and we will be using the same implementation here also. So I will not be writing that implementation from scratch in this video, I will just be copy pasting. So here in multiple linear regression implementation that we had done, this was the implementation for a gradient descent algorithm. So let us copy this out and we will make some changes in this. So I'll copy this and I will go back to my logistic regression file and paste this down here. And now let us go above and make some changes. So the function name is gradient descent algorithm. So here I will say training logistic regression model using gradient descent. I will again keep the max iteration same, 4000, and I will set a boolean which will let the program know whether the gradient descent algorithm was able to find a local minima, that is, it was able to find the point of convergence where the algorithm converges and you get an optimal value for your parameters of your model. So I will set up a boolean has converged false. Then we have the variable for rows count that holds the number of data points in the current dataset, x of 0 dot shape 0. So here we have an initial value of parameters, so let us keep this to 5 zeros, and then the initial value for error or the cost based on the initial values of parameters. So for that I will define an error function. So change that to our error function. This will take on the predictors collection, the collection of response variables, and your parameters collection. And then here we can say initial value of error. Then here we will set I as 0. While we haven't reached convergence, we will compute the gradients just like we did in the implementation for multiple linear regression. For each training sample we computed the gradient, and we will be using the same formula for computing the gradients, and we will be defining this function in just a minute. So predicted value for specific row, and here we will be getting 4 gradients. So let us remove these ones. So we are having 4 gradients now. because here we are having 4 predictors. So we will be computing the gradient along each dimension that we are having. So along each predictor we will be computing the gradient, and that is why we will have 4 gradients. And then what we are doing here is that we are computing the new parameters according to the current value of gradients. So remove these 3 because they are not required, and then you update your parameters with the temporary values of the predictors that you are getting. So each time iteratively you are updating the values of your parameters, and you are getting new values for our parameters, and we want an optimal value for each parameter. So here we are having 4 parameters, so we want optimal values for each of the parameter that we are having. And in case you are having some difficulty in understanding this, I have already covered this in great depth in the video on multiple linear regression. The link for that video can be found down below. And here also we will compute the error. So we will define the error function in just a minute. And here, if I modulo 250 is 0, then we will be printing the iterations. So current value of error based on updated values of model parameters, and then you will update the error value to current error, and then you will increment the iteration by 1. And once the iterations max out, then the training process will get completed, and we'll set the has converged boolean to true. And once it is set to true, whatever optimal collection of model parameters we will get, we will return them here. So next we will define this error function and the predicted value for specific row. So I just realized that I forgot to compute the gradient for one more input predictor, because as what you can see from the code, we are having 4 predictors and we are using only the 3 predictors. We need to use the 4th one as well, so we'll need one more gradient. So I will say I'll copy this out, paste it down below, change this to G4 and change this to X3I. And corresponding to the current gradient that we now have, we'll have a temporary value for our model parameter as per the equation for gradient descent that we had discussed in the concept video. So I'll copy this and paste it down below. So change this to temp4, m4 minus learning rate into G4. And now update the 5th model parameter as well. So now after making these changes, let us write the function for error and the predicted value for specific row. So this function and this function, because gradient descent requires this in order to give some result to us. So I will go right above the gradient descent function, and I will define a function for error calculation. So I'll leave a docstring comment here and say error calculation. So in the video of logistic regression, our concept video, we had discussed about the error function to compute the value of cost function. So let us define a function for it to compute the error. So I'll define a function, name it as error, and this will basically receive the collection of predictors, the collection of response variables, and the model parameters collection. So I'll define a variable e and set that to 0. So 0 will be the initial value. I will use a loop and say for I in the range x0 and the shape of it. So now using this I index, so we will be iterating over the entire dataset row by row, and using the index I, we will be able to refer the predictor values that are sitting in a particular row of the dataset, refer these values, and we will compose a b value which is required to be passed to our sigmoid logistic regressor function that I will define in just a minute. So I can say predicted value, and I will call the sigmoid logistic regressor function that we will be defining in just a minute, and I will say m0 plus m1 into x0 x0i. Now x0 basically refers to the first column, and using the I index you will be able to read the value of predictor that is sitting in the first column in the very first row for the very first iteration. Then I can say m2 into x of 1 and I. So in the second column and I is 0, then second column first value. If I have 1, then x11 will denote second column second value, and so on. So you can easily interpret it. We are going row by row. So I'll not waste much time here, and I will copy this out multiple times. So plus, change this to M3 and x2i plus M4 x3i. So that is the value of p that we'll pass on to our sigmoid logistic regressor function, where we will be applying the equation. So now once we have a predicted value for a row that we are currently on, we can then get the actual value for that row using the label, the target response variable that we are already having in the dataset. Because remember that logistic regression is a supervised machine learning technique, so that the labels will help us in training our model. So to get the actual value, I can say actual value y, and I will say I. So y of I will refer to the actual value. That is the last column, which is the response variable collection. So each time you are going over the dataset row by row and grabbing these values, you are using all the predictors for a particular row to make a b value, and you are passing that to a sigmoid logistic regressor to get a predicted value. And using the last column of a particular row, you will be grabbing a value for a target or a label, and you get the actual value from that row that you are currently on. So now to compute the error, I will use the exact same equation that we discussed in the concept video of logistic regression. So I will say error plus -1 into actual value that we just computed for a particular row into np log. So numpy log, you're taking the logarithm for the predicted value, minus, and then I will say 1 minus actual value into numpy log 1 minus predicted value. So now we have the error. So now once the entire data set is exhausted or consumed, that is, we have encountered each and every row of our data set, we can return the error that we just computed. So I will return the error here. Okay, so change this to E. So this is our error function. Secondly, we need to define a function which is required for our gradient computation in the gradient descent algorithm, that is right here. So predicted value for specific row. So this takes on a collection of predictors that we have in each row of our dataset, represented by capital X. The current row for which we want to compute the predicted value, which is denoted using small I, and the collection of our model parameters. So let us define the function predicted value for specific row. So let's copy the name here, and I will go right above the gradient descent and right below the error function, and I will leave a docstring comment here, predicting value for a specific row. So I will define the function. So we will use the sigmoid logistic regressor function here also that we defined above, and pass on the value of b, which is this. We will use the same value, this one, and I will say return, invoke the function sigmoid logistic regressor, and pass on this to that. So this is our predicted value for specific row function. So now we have to define this function, which is sigmoid logistic regressor. So I will go right above the error function and leave a docstring comment here. So sigmoid logistic regression function. So I'll say def, and this will take on a value of b, and this will return 1 upon 1 plus np dot exp minus 1 into b, like this. So now we have defined all the functions required for performing gradient descent. The one step that remains is to split that dataset into training dataset and the testing dataset. And what strategy I'm going to adopt is that in the entire dataset that I'm having, I will select first 5 rows for training, then next 45 for testing, then next 5 again for training, next 45 for testing, and that is how a split will look like. So in all we will be having 15 rows for the training process and 135 rows will be used for the testing process, where we will make predictions using logistic regression. So now this is clear, let us make the splits. So right below here I will say training dataset, and we will make a training set for our predictors first. So train underscore x, and I will say np.concatenate. So I will basically extract out all the predictors from the rows. So I will extract out all the predictors, that is these, from all the rows, and will basically form a training collection or the training set for predictors. So train underscore x, using the strategy that I just told you. So what will happen is that from all the rows, I'm going to take first 5 rows for the training process, or the predictors for the first 5 rows for the training process. Then side by side I will also define the testing dataset for our predictors. So np.concatenate, and as I told you that first 5 rows will give us predictors that we are going to use for training dataset. Then colon represents all the rows, and then I will select the next 45 rows after the first 5 rows. Okay, so 5 from the row that is starting at index 5 to 50. So 50 is exclusive, so 5 to 49 for our testing portion. And then right here I will say 50 to 55. This will be used for our training process, so training data. And then right here I will say colon 55 to 100 and 100 to 105, and lastly row number starting from 105 to 150, and we are grabbing all the predictors. And it will take a second argument which I will define the axis. So the axis will be set to 1 here and 1. So now similarly we will do the same process for the training set of our response variables, and here also we will be having 15 response variables which will follow the strategy that I just told you for getting the training set for response variables. So train underscore y, and I will say np.concatenate. So we will grab the response variable for the first 5 rows, that is the last column. We are taking on the last column values for the first 5 rows starting from index 0 and going forward to index 4. Then next 45 our response variables will be used for our testing dataset. So we will omit that here, and 50 to 55. And then we will have 100 to 105. So we will be omitting 55 to 99 from our training, and it will be included in our testing dataset portion. Okay, so it will serve as response variable for our testing dataset 105, and I will pass second argument as 0, and then test underscore y, np.concatenate y. So 45 values, 45 response variables we are again grabbing from the last column of our dataset, starting from the row marked by index 5 and going forward to index 49, omitting the 50th one because this index is exclusive as I already told you. Now 50 to 55 is used for training, so we will start with 55 now and go forward to 100. So 55 to 99 because 100 is exclusive, and then 105 to 150, and lastly I will pass the second argument as 0. So these are our splits that I wanted to do. So now our splits for the dataset is done. Now let us invoke the gradient descent function and pass the training data for the predictors for entire dataset as well as the training data for response variable, and we will use a point1 as the value for our learning rate. So this function will return us an array of coefficients, and I will store that in a variable name as coefficients. So I will say gradient descent algorithm. This will take on the training predictors and train underscore y, training predictors, training response variables, and the learning rate as 0.1. So now let us print the coefficients that we get. So I will say print coefficients of our model, and let us try to run the 5. So right below here I will say python logreg.py and press enter, and now you can see our iterations are running. So we are getting current value of error based on the error function that we had defined. So you can see we are having 5 values for our model parameters, that's the coefficients of our model. Okay, and the training process halted as the number of iterations that we had defined are maxed out. So now let us define an empty array of predictions. So I will say predictions, and now we will be making the predictions for new data points. So now what I want to do is I will iterate over the predictors that we have in our testing portion. For I in range 0, I will take on the transpose for our testing portion of our predictors and use the shape method on that. So we discussed that logistic regression works on the concept of probability, and that probability is a continuous variable that lies between 0 and 1. So I'll define a predict probability function that will take on an array of coefficients and the current testing data points predictors, and will spit out the probability which we will use to assign a class to a new testing data point. So I will say probability and set that to a function, so predict probability, and this will receive coefficients and the new point for which we want to make the prediction. So I will say np.transpose test underscore x and pass on I, because we want to test the performance or statistical power of prediction of our model for the testing data points, which are those points on which our model was not trained on. Okay, so that is what was the need for making this testing portion, and now we are utilizing that. We'll pass on the point or the predictors that represent the testing portion, and for that we will compute the class. Okay, but before predicting the class, we'll have to predict the probability, and based on the probability that you get, we'll compare that with some threshold value and assign a class of setosa or non-setosa to the data point. So that means that whatever probability you are getting or you will get, we'll pass that to the classify function that I will be defining in just a minute, and this will use the concept of some threshold value based on which it will assign a class to the new data point. And this we have already discussed in the concept video, so I'll just append the class that we get from the classify function like this. So I'll say predictions.append, and you will get a class by the classify function, and this classify function will receive the probability that you're getting here as an argument, and you will append the prediction to the predictions array. And down here, let us change the array of predictions to an umpire array. So I'll say predictions np.array predictions, and then we will print the predictions to the terminal. So print predictions. So in order to make this loop functional, let us define the predict underscore probability function and the classify function. So right below our predicted value for specific row function, I will define the predict probability function to predict the probability, and it will take on an array of coefficients and a predictors collection. And remember that each point will have, or each row will have its own predictor values, which are represented by the first 4 values of a row. The 5th one is of course your response variable, so I will use an array for that. So in all, you can easily see that Rx will be a list of lists. So the outer list may contain a single row, which means a single list representing a single point, or the outer list may contain multiple points that means multiple lists, because I already told you that each point is represented by a list. That is how we had stored the entire dataset in a read data function, as you can see here. We will have to check for that whether we are making a prediction for a single point, for a single test point, or for a collection of such test points. So I'll define a function right here, predict probability, and this will take on the coefficients that we determined right below and take on our collection of predictors. So first I will pull out all the model parameters one by one in respective variables. So I'll say m0 and set that to coefficients of 0, and let us copy this multiple times, change this to m1, coefficients of 1, 2, 3, 4, m2, m3, m4. So now let me define an empty array that will hold our predictions. So I will say predictions, set that to an empty array. So if we have a collection of test points for which we want to make predictions, that can be checked by using this if condition, that if length of your predictors collection is greater than 1, that is, you are having the predictor set for multiple points, for multiple test points for which you want to make a classification, or for which you want to classify a bunch of points into its respective category. So for multiple points we can say if the length of our predictors collection is greater than 1, then for each point that we are having in this variable, so I will say for x in x. So now this small x represents the inner list, okay? So your x, as you can see, will be points. So point, point, point. So it can be multiple such points, okay? And each point in itself is a list that has its predictors. So for now I'm passing any random value, but you can easily see that from your dataset. And this will represent sepal length, sepal width, petal length, and petal width. So these are your predictors, and this entire thing is a row or a point. This entire thing is your x, and we are checking for that here. So for x in x will denote that you are currently on a point. So this small x will refer to a point in each iteration, and then you can access the values that are sitting in the point. And these values are predictors, of course. So I hope this is now crystal clear. So for each point that is represented by a list that is small x inside the outer list, we can access the predictor values within the inner list, and then we can compute the value of p for each row, each new data point for which we have defined this function. So this x contains predictors for all unknown points or new points. So I will define the b value, and I will go right above, and we will be using this only. So I'll copy this out and make some changes here. So it will be small x, you know, represents a list. To access the first predictor you say x of 0. To access the second predictor you say x of 1 and x of 2, and for the last predictor x of 3. And I will wrap this in parentheses. Here it will be m0, m1, because we are having the coefficients with us. We pulled out that here, so we have separate variables for that, and m2, m3, and finally m4. So this is our b value, and now whatever value of b you are getting, you will pass that to the sigmoid logistic regressive function, and this will give us the result. So I'll define a variable result, sigmoid logistic regressive, pass on the value for b, and I will log x of 0, just for your reference, x of 1, x of 2, x of 3, b, and result to the terminal. And we will also append the prediction to our array of predictions. So prediction, not prediction, it is result here. And now finally we can return the array of predictions, which hold the predictions for all the test points that we pass to the function. So I'll go right below here and say return predictions. So for the other case, if we had a single test data point or the predictors for a single row, which is in our test dataset, we can access that using the index 0 because we will be having a single point. And then each predictor for that point, which is itself a list, because you know that point is a list, will help us in forming a value of p. We'll pass that to the sigmoid logistic regressive function, just like we are doing here. But the difference is now we are working for a single point, and this is working for a collection of such new points. So we'll pass that to the regressive function, and this will give us the prediction for that new point. So if we have just a single point, if we have only a single test data point, we can extract that by saying x as x0. Okay, so now we have the inner list that represents that single data point or single test point. And now to get the prediction, sigmoid logistic regressor will pass this value of p, this complete value of p, which pertains to the single point that we are working on, and pass it here. And finally, once we are done with the prediction, we can return y. So now, before testing our functionality, let us define the classify function that will take on the predicted probability and the threshold value, based on which it will assign a class to the new unknown data point. So class assignment to the new data point. So I'll say classify, and this will take on a predicted probability and some threshold value. And I will set the threshold value as 0.5, which is a default argument. So I'll not be passing a value for that. It will take a default value of 0.5. And then if the predicted probability is greater than our threshold, then we will return 1, indicating that it is a setosa, else it is a non-setosa, which is denoted using 0. So now let us test the functionality by running our code. I will go right below. Now let us run our script file. So python logreg.py, and now you can see our iterations are now running. Okay, so here are the predictions that we are getting for our testing dataset, because we know that the testing dataset holds 135 points, which are new points on which our model was not trained on, but we are testing its performance on these points. And for these points, the results are that these many points belong to the class of setosa, and these many points belong to a class of non-setosa. So finally, let us evaluate the performance of our logistic regression model. So we covered the performance evaluation metrics in great depth in one of the previous videos, where we learn about the accuracy and its limitation, precision, recall, and F1 score, and also about the confusion matrix in great depth. In case you haven't seen that video, it's highly recommended to go over that video first before you proceed with the code that I'm about to write now. So to evaluate the performance of our logistic regression model, what I will do is I will define a evaluate performance function that will take on our testing dataset, response variables, and the predictions that we just got, evaluating the performance metrics for the model. And what we expect to get from the function is accuracy, precision, and recall. And we'll call evaluate performance. And the evaluate performance function will take on our testing data response variables, test underscore y, and the predictions that we obtained on line number 183. And once we get them, we can print them here. So accuracy will be accuracy, and precision will be precision, and recall will be recall. So let us go right above, and right above our gradient descent function, evaluating the performance by computing elements of the confusion matrix. So based on the confusion matrix that I had discussed in a great depth, we will be computing accuracy, precision, and recall performance evaluation metrics. So for that, we will write the evaluate performance function that takes on our testing dataset response variables and our array of predictions. So I will say def evaluate performance test underscore y and the predictions. So now we have to obtain the true positives, false positives, true negatives, and false negatives. I have discussed them in great depth in the video on performance evaluation metrics for classification model. The link for that video can also be found at the top right corner of this video. So we will be defining a function and we will name it as give confusion matrix elements, and I'll pass on the testing dataset and the predictions as well. I will get true positives, false positives, true negatives, and false negatives. And I will call the function give confusion matrix elements that we will be defining in just a minute, and pass on the testing dataset response variables and the predictions. So let us first define the function for confusion matrix elements. So now based on the actual response variable for a test data and the predictions that we got, let us compute true positives, false positives, true negative, false negatives, and return them. So for that, I will define the function def give confusion matrix elements, and this will receive the testing dataset response variables and your predictions. I will leave a docstring comment here computing true positive, false positive, true negative, false negative, these things. So let me just copy them because we will be returning them in the same order only. So we know that true positive is when the model gave a prediction and that prediction is the same as the actual one. False positive is when the model gave a prediction and the actual result was different from that. True negative is when model gave a prediction that was for a negative class and actually also it was a negative class. And false negative is when the model gave a prediction for negative class but in reality, in the actual sense, it was a positive class. We have discussed this in great depth. Definitely check out that video. So I will say true positives, and from the predictions that we are getting, I want those predictions which represent the response variable as 1. Okay, that is those which are actually setosa, and the model also predicted those points in the category of setosa. So we can say true positives, where the true positives are 1, that is it's a setosa. And finally true positives, so we need the count for that, okay, and not the array. So for that I can use the shape method, and this will return us the number of true positives. And I will copy these 3 lines right below, change these things to true negatives. So true negatives and a testing value or the response value as 0 because we are testing for a true negative. So for getting the false negatives, I can say 90 minus true negatives, and this we already know from the column of confusion matrix. So you can relate this to that and you will be able to understand it, because the total count for false negatives plus true negatives will be 90. And to get false positives, I will say 45 minus true positives. So this you can easily relate from the confusion matrix. And finally we can return them as a list. So let us return them in the same order in which we are getting them here. So return as a list and paste it right here. So this function is now done. Let us complete our evaluate performance function. So now we have the value for these terms, so we can compute the accuracy by saying computing the accuracy for the model. Accuracy will be true positives plus true negatives divided by true positives plus true negatives plus false positives plus false negatives. So now to compute the precision, I will first find the precision for the positive class. I will leave a comment here finding the precision for the positive class, precision underscore 1, and this will be true positives divided by true positives plus false positives. And now similarly I can find the precision of the negative class by saying, so I will copy these two lines, paste them right below and change this to negative. So, and I will use multiple cursors here, so control and use your mouse, or so true negatives divided by true negatives plus false negatives, you will get the precision 0, which is the precision for the negative class. So now in order to find the value of precision, we can say precision, and this is the average of the precision of positive class and the precision of negative class. So precision will be precision of 1 plus precision of 0 divided by 2. And now let us compute the recall. So let us first find the recall of positive class. Without wasting any time, I will copy these 3 lines and paste them right here. Change this precision to recall, and right here recall for the positive class, which is recall underscore 1, and recall for the negative class, which is recall underscore 0. And let us make some changes here now. So recall for your positive class will be true positives divided by true positives plus false negatives. So this will be negatives. So let me copy this and change it here. And this will be positive. So recall for your negative class will be true negatives divided by true negatives plus false positives. Okay, so this will be positives. And now in order to find the value of recall, we can say recall is your average of recall of positive class and recall of negative class. So again apply multiple cursors and change this to recall. Okay, so it's done now. So now let us return the evaluation metrics that we just computed. So I'll multiply each metric that we obtained here by 100 and round it to 2 places of decimals. So now let us return the accuracy. So return, I'll use the round function, pass on the accuracy, multiply that with 100 and round that to 2 places of decimal. Let us copy this and paste it 2 times. So I will change this to precision and I will change this to recall. So finding the F1 score, I will leave that as an exercise for you. Although it is not required for our model analysis, let us try to run our code to see whether we are getting the values or not. Python logreg.py. So our iterations are now running. Okay, so I think there is an error here. It says true negatives are referenced before assignment. Okay, so we made one mistake here. There will be equal to here. So now let us try to run the code again. So our iterations are now running. Is not subscriptable. On line 119, we forgot to change this from positives to negatives, because here we are working on true negatives and we are checking for those classes where true negatives are 0. Okay, so let us try to run the code again. So as you can see, we are getting a result of accuracy as 100, precision as 100, recall as 100, and I think the data is getting overfitted here. So this is not a correct result for that. So let us change the number of iterations. As we have increased the number of iterations, it is taking more time to converge. It's a high possibility that it may be overshooting or diverging to some other value. And that is why it gives us false impression of our performance evaluation metrics. So what I will do is, for our gradient descent function, instead of using max iterations as 4000, let us use some other optimal value say 100. So I will reduce the number of iterations from 4000 to 100. And now let us try to run the code. And we will learn about overfitting in coming videos. So don't worry for that as of now. Okay, so you can see we are getting an accuracy of 98.52, precision as 98.89, and recall as 97.87. So this was all about the video on logistic regression. So if you liked the video, do give it a thumbs up, subscribe to the channel, and I will see you guys in the very next video.